Now, the theorem and the statement is that if sequence Sn is a convergent sequence of real numbers, convergent sequence of real numbers, then limit supremum of sequence Sn is limit of sequence Sn. When the sequence Sn is a convergent sequence, that means for every convergent sequence, limit supremum of the sequence is same as limit of the sequence. So the proof. So for both these things, we have to use the definition of supremum and definition of limit of a sequence. So let us suppose, let limit of sequence Sn as n tends to infinity is L, because it is given that the given sequence Sn is a convergent sequence. So let us assume it has a limit L. That means what? By the definition of limit, then for any given epsilon greater than 0, there exists some positive integer n. There exists a positive integer n such that the difference Sn minus L is less than epsilon, and it is true for all integer greater or equal the positive integer n, right? And it means what? L minus epsilon is less than Sn is less than L plus epsilon by using the property of absolute value function, right? So it means what? Therefore, if n is greater or equal n, then this L minus epsilon is an upper bound, for what? If Sn is less than L plus epsilon for all n greater or equal n, so this L plus epsilon, it should be what? An upper bound for what? All n greater or equal n. That means it will be upper bound for which set? For the set Sn, then the terms larger than or more than Sn, Sn plus 1, Sn plus 2, and so on, right? But L minus epsilon is not an upper bound, for this set, right? But then it means what? Therefore, by the previous theorem, so as it is bounded by L plus epsilon, and if this is the upper bound, so we consider Mn to be, so let Mn to be a least upper bound of this set Sn, Sn plus 1, Sn plus 2, and so on. So what this Mn would be? So as this thing is an upper bound and sequence Sn is bounded by this, so least upper bound of this sequence will definitely lies between L plus epsilon and L minus epsilon, right? And what we know? Limit of this least upper bound is nothing but limit of supremum of sequence Sn as n tends to infinity. This is why, because the sequence Sn is convergent, and we have seen this thing of in the definition of supremum, right? So it means what? So as sorry it, here it is limit, so it implies what? L minus epsilon is less equal limit of supremum of Sn, which is less equal L plus epsilon, which is less equal L plus epsilon. And now as it means that, right, so by definition of limit it means that this implies supremum of Sn minus L is less than epsilon. So we have shown that limit of supremum of Sn is L, and we are done. So let us go to the next definition. Now we define a limit inferior. So for a sequence Sn is bounded below then if it is bounded below, then it should have a lower bound and a greatest lower bound. Then the set, let me call it as X, which is having the term letter on Sn plus 1, then Sn plus 2, and it should have a lower bound and a greatest lower bound also. So we let this Mn to be a greatest lower bound of that set X. Sn, the terms are Sn plus 1, Sn plus 2, and so on. So definitely, so if we consider this Mn and the Mn plus 1, so what the comparison is? So we are considering the lower bound and greatest lower bound. If this Mn plus n will be a greatest lower bound of Sn plus 1, Sn plus 2, Sn plus 3, and so on. So compare these two things, Mn and Mn plus 1. So definitely it is this thing will be less than or equal to, less than or equal to. So it is a non-decreasing sequence. Now therefore this sequence Mn is a non-decreasing sequence. And hence a non-decreasing sequence. So either it, therefore Mn either converges or diverges to infinity. In non-decreasing sequences, either diverges to infinity, right? So the definition of let Sn be a sequence of real numbers that is bounded below and we have defined Mn to be a greatest lower bound of the set Sn, Sn plus 1, Sn plus 2, and so on. So the first thing. If this sequence Mn converges, so then we define limit of infimum of sequence Sn when n tends to infinity is same as limit of sequence Mn when n is very large. And the other thing is that if sequence Mn diverges to infinity, then we can write this thing as limit of infimum of sequence Sn is to be infinity. So the definition of limit inferior is if sequence Sn is a sequence of real numbers, that is not bounded below, then we write limit infimum of or inferior of sequence Sn is to be minus infinity because it is not bounded below. So examples. Example 1. Sequence Sn is minus 1 raised to n. So what can be the limit inferior when n is large of this sequence will be minus 1. So similarly, if we consider the sequence Sn to be n, then limit inferior of this sequence n will be Sn is n will be infinity. And the next example, if we consider it to be minus n, then limit inferior of this sequence will be minus infinity, right? And so on. So the theorem with the statement is that if sequence Sn is convergent sequence of real numbers, then limit inferior of sequence Sn is same as limit of sequence Sn, and we can show this proof which is analogous to the previous theorem, and the proof is analogous to our previous theorem. So try to show this thing. Okay. Now the next theorem is that if sequence Sn is a sequence of real numbers, then for every sequence, limit inferior of sequence is less equal limit superior of sequence Sn. So this is the statement of the theorem. So now consider proof. Let Sn be a bounded sequence. So if the sequence Sn is bounded, sequence of real numbers, right? So if it is a bounded sequence, then what we can do? So then what is this? Consider set x with these terms Sn plus 1, Sn plus 2 and so on. Now consider the least upper bound of this set, least upper bound of x and greatest lower bound of x. So if we consider least upper bound, so it is a non-increasing sequence. If we consider greatest lower bound, it is a non-decreasing sequence, right? So greatest lower bound is always less equal least upper bound, right? And what we have defined, this least upper bound of this Sn plus 1 and so on is to be a Mn, right? And we have defined similarly a greatest lower bound of Sn plus 1 and so on is to be a small mn, right? So thus, therefore what we get, the small mn is less equal a mn, large mn. Right. Yes, it is Mn is infimum of sequence Sn. Therefore, we are done. So this is nothing but we have defined it to be a limit infimum of sequence Sn. Limit infimum of sequence Sn is Mn and limit superior of Sn is the large Mn. So this was the case if the sequence Sn is a bounded sequence. Now let's consider sequence Sn is not bounded sequence. Then what happens? Is it true? Is the result hold for this case also? So if it is not bounded, then either limit superior of Sn is infinity. If Sn is not bounded, then its limit superior is infinity or limit inferior is minus infinity. Is minus infinity. And obviously the result follows. So if it is not bounded, either this limit is minus infinity or limit superior is infinity. That means it will hold. Therefore, in both the cases, limit inferior of Sn is less equal limit superior of sequence Sn. And one remark is there, if sequence Sn is a convergent sequence, therefore if it is convergent, then limit of sequence Sn is L, say, right? And in this case what happened? limit superior, if the sequence is convergent and it converges to some limit L, then limit superior of sequence Sn will be same as L, and it will be also same as limit inferior of sequence Sn. So the next theorem is that if sequence Sn is a sequence of real numbers, and if limit superior of sequence Sn is same as limit inferior of sequence Sn, where L is a real number, then sequence Sn is convergent and limit of sequence Sn is L. So it is a very easy part. You can do yourself, because in this remark we have seen that if Sn is a convergent sequence, then limit superior and limit inferior are same and they are equal to the limit of the sequence for a convergent sequence. And this theorem is nothing but converse of this remark. If limit superior and limit inferior for the sequence Sn both exist and equal, then the sequence is convergent and is also converges to the limit superior or limit inferior, right? So you can try yourself. It is just the application of the definition. The next theorem. If sequence Sn is a sequence of real numbers, and if limit superior of sequence Sn is infinity, which is also same as limit inferior of sequence Sn, so both the limit superior and limit inferior exist and equal to infinity, then sequence Sn diverges to infinity. So it is also a same application of the definition, that both the limit superior and limit inferior exist and equal to infinity, so the sequence has to be limit infinity. That means it should diverge to infinity. The proof is also very easy and small. So let limit inferior of sequence Sn is infinity. So it means what? Limit is infinity. It means for given any positive real number m, there exists some positive integer n such that, as it is limit inferior, such that the greatest lower bound of the sequence x, Sn plus 2 and so on, so it should be greater than m, right? Limit inferior exists and it is to be equal to infinity. It is true for all n greater equal n. So this implies that this m is a real number, m is a lower bound for set x. So the sequence Sn is definitely greater than m for all n greater equal n. So it implies that, it says that sequence Sn diverges to infinity. So this is just an application of the definition. The next theorem. Okay, we stop here. We'll see this part later on.